Welcome to G-Fun Facts Online. When you think of an earthquake, you probably picture California or Japan, places right on the edge of the Earth's great tectonic plates. These are the planet's fault lines, where massive pieces of the Earth's crust grind against each other, unleashing incredible energy. But what if I told you that some of the most powerful and surprising earthquakes in history have happened thousands of kilometers away from these boundaries, in places considered geologically quiet and stable? Today, we're diving deep into the Earth's unruly interior to uncover the mystery of intraplate earthquakes, the tremors that shake the very foundations of what we thought we knew about our planet. To understand what makes these rogue earthquakes so strange, we first need a quick refresher on the basics. The Earth's outer shell, the lithosphere, isn't one solid piece. It's broken up into giant tectonic plates that are constantly moving, floating on a sea of semi-molten rock below. Think of them like massive rafts on a slow-boiling pot. The action happens at the boundaries where these rafts meet. At convergent boundaries, two plates collide. One often slides beneath the other in a process called subduction. This creates immense friction and pressure, leading to the most powerful earthquakes on the planet, called megathrust events. The 1960 Chile earthquake, the largest ever recorded, was one of these. Then you have divergent boundaries, where plates pull apart. Molten rock rises to create new crust, like at the Mid-Atlantic Ridge. This process also causes earthquakes, though usually less powerful. Finally, there are transform boundaries, where plates slide horizontally past one another. The San Andreas Fault in California is the textbook example, where the Pacific Plate grinds past the North American Plate, building up stress that gets released in jolts. Over 95% of the world's seismic energy is released at these three types of boundaries. They are the well-understood, if terrifying, consequence of plate tectonics. The 2004 Indian Ocean earthquake and the 2011 Tohoku quake in Japan are tragic reminders of the power at these edges. This is the standard model, the one we teach in geology class. But it doesn't tell the whole story. Now, let's venture into the unknown. Intraplate earthquakes. As the name suggests, they happen within a plate, far from the chaotic action at the edges. Imagine a massive earthquake striking the central United States, or a tremor shaking the East Coast, rattling buildings in Washington, D.C. It sounds like a disaster movie plot, but it's happened, and it will happen again. These events are rare, accounting for only about 5% of the Earth's total seismic energy release, but they are disproportionately dangerous. Why? Because cities in the middle of tectonic plates are often built with zero consideration for seismic hazards. Their buildings aren't reinforced, and the public is completely unprepared. One of the most fascinating differences lies in the stress release. At plate boundaries, the rocks are relatively weak and break easily, leading to what seismologists call a lower stress drop. But in the interior of a plate, the rock is older, colder, and much stronger. It can accumulate immense strain over millions of years. When it finally snaps, the release of energy is far more abrupt and efficient. This results in a higher stress drop, producing ground shaking that is more intense and can travel much further than an interplate earthquake of the same magnitude. So, a magnitude 5.8 quake in Virginia can be felt across a wider area than a similar-sized quake in California. It's a case of the quiet ones being the most powerful. So what could possibly cause the stable heart of a continent to rupture? For a long time, this was a major puzzle, but scientists now believe it's a combination of ancient history and modern stress. A leading theory points to the reactivation of ancient faults. Continents aren't smooth, uniform blocks. They are geological patchworks, stitched together from ancient landmasses over billions of years. Buried deep within them are the scars of this history, ancient fault lines and failed rifts. These are places where, hundreds of millions of years ago, the continent started to rip apart, but the process failed, leaving a permanent zone of weakness. These old wounds, dormant for eons, can be reopened. Think of it like having an old injury that aches when the weather changes. The weather in this case is the constant stress that flows through the entire tectonic plate. The very same forces that drive the plates at their boundaries, the push from mid-ocean ridges and the pull from subducting slabs, transmit stress deep into the continental interior. As the plate moves over the curved surface of the Earth, it also bends and flexes, creating weak points. But the pressure doesn't just come from the sides. It can also come from below. Hot plumes of rock rising from the Earth's mantle can heat and weaken the lithosphere from underneath, making it more prone to cracking. Then there are more localized triggers. A big one is isostatic adjustment. At the end of the last ice age, about 10,000 years ago, massive ice sheets weighing trillions of tons melted away. Regions like Scandinavia and North America are still slowly rebounding upwards from this weight loss, and this crustal movement can trigger earthquakes. Water also plays a role. Rainwater can seep miles into the crust, increasing the pressure in the pores of the rock. This increased pore pressure can act like a lubricant on an ancient fault, making it easier for it to slip. And, of course, there's us. Human activity is now a recognized trigger for earthquakes. The large-scale injection of wastewater from oil and gas operations, especially fracking, has been directly linked to a surge in seismicity in places like Oklahoma. Pumping massive volumes of fluid deep underground can do the exact same thing as the rainwater. It lubricates ancient faults and wakes them up. Building massive reservoirs for dams or conducting large-scale mining operations can also alter the stress on the crust enough to induce a tremor. History provides some dramatic case studies. Let's travel back to the winter of 1811 to 1812 in the central United States. A series of massive earthquakes, some estimated at magnitude 7.0 or higher, struck what is now known as the New Madrid seismic zone. These quakes were so powerful they were felt over 2 million square miles. Church bells rang in Boston, and sidewalks cracked in Washington, D.C. The quakes were so violent, they temporarily changed the course of the Mississippi River and created new lakes. This was the dramatic reactivation of a 500-million-year-old failed rift system, a deep scar in the North American plate. Fast forward to 1886 in Charleston, South Carolina. A magnitude 7.0 earthquake devastated the city in a region with no prior history of major quakes. It was a wake-up call for the eastern U.S., proving that no area was truly safe. Even today, the exact fault responsible is still debated, highlighting how difficult these features are to find. A more modern and tragic example is the 2001 Gujarat earthquake in India. This magnitude 7.7 monster struck far from the Himalayan plate boundary, killing over 20,000 people. The town of Bhuj was almost completely destroyed. The quake happened on a previously unknown, deeply buried fault, and the catastrophe was made worse because the buildings were simply not designed to withstand shaking. And many of you might remember the 2011 earthquake in Mineral, Virginia. At magnitude 5.8, it wasn't a giant, but its location in a densely populated area meant its effects were widespread. It damaged the Washington Monument and was felt from Canada to Georgia, a potent reminder that even moderate intraplate quakes have major consequences. Even a small magnitude 4.9 quake in Lataye, France, in 2019 surprised scientists. It was extremely shallow and occurred on a fault thought to be inactive for millions of years, causing significant damage and raising new questions about what can trigger these events. Unraveling these mysteries is a massive scientific detective story. The prime tool is the global network of seismometers, which record ground motion. By analyzing the waves from a quake, scientists can pinpoint its location, depth, and magnitude. But for intraplate zones, they need denser arrays of these instruments to detect tiny microquakes that can help map out the hidden fault structures. Another revolutionary tool is GPS. High-precision GPS receivers can measure the slow, subtle movement of the ground with millimeter accuracy. Over years, this data can reveal where strain is building up within a plate. Geologists also hit the field, looking for clues from the past. They search for offset layers of rock, fault scarps, or features called sand blows, which are created when a quake liquefies sandy soil. By dating this evidence, they can reconstruct a fault's history, but often, the evidence has been eroded away or is buried deep underground. To see what's buried, scientists use techniques like seismic reflection, which is like a geological ultrasound. They send sound waves into the ground and analyze the echoes to create images of the subsurface, revealing hidden faults and ancient rifts. Finally, all this data is fed into powerful computer models. Scientists can simulate the forces acting on a plate to test hypotheses and understand how the complex interplay of factors can lead to a sudden, violent rupture in the middle of a continent. The greatest danger from intraplate earthquakes is their sheer unexpectedness. Communities are unprepared, building codes are inadequate, and the solid ancient rock of continental interiors transmits seismic energy with terrifying efficiency, meaning the shaking is felt over a much larger area. Predicting them is an even bigger challenge than for their plate boundary cousins. The faults can be dormant for tens of thousands of years, leaving no historical record to go by. So what's the path forward? Research is focused on getting better at finding these hidden faults using advanced imaging and denser monitoring networks. Scientists are building more sophisticated computer models to understand the complex triggers, from mantle dynamics to the role of fluids in the crust. But perhaps most importantly, we need to communicate the science. By raising awareness of this hidden hazard, we can help communities prepare. The ground beneath our feet is not as solid as it seems. It is a dynamic, complex, and sometimes unruly system. By continuing our detective work into the Earth's interior, we not only learn more about our planet, but we also learn how to protect ourselves from its most surprising fury. Thanks for listening to Fun Facts Online.